Far beneath the Pacific Ocean lies one of the most extreme places on Earth, a tectonic boundary where the planet is ripping itself open faster than anywhere else on the surface. Known as the East Pacific Rise, this hidden scar creates vast stretches of new ocean floor every year, releasing immense heat and magma in near total silence. It doesn't erupt with spectacle or shatter cities. Instead, it reshapes the planet continuously, unseen. But could activity here quietly transfer stress through the Earth, nudging nearby faults closer to breaking? Let's find out. Stretching across the eastern Pacific Ocean, from the Gulf of California past the Galapagos region and deep into the Southern Ocean, the East Pacific Rise is one of the most important yet least visible geological features on Earth. It forms part of the global mid-ocean ridge system, a vast chain of underwater mountains that wraps around the planet like the seams of a cracked shell. These ridges mark places where tectonic plates move away from each other, allowing molten rock from deep within the mantle to rise, cool, and solidify into new oceanic crust. This slow but relentless process has created nearly all of the seafloor that exists today. What sets the East Pacific Rise apart is how fast it operates. Along much of its length, the Pacific Plate is pulling away from neighboring plates such as the Nazca Plate and Cocos Plate at rates of up to 15 to 16 centimeters per year, the fastest spreading speeds observed anywhere on Earth. That speed fundamentally alters how the crust forms and behaves. At slower ridges, new crust forms slowly, giving it time to cool, harden, and crack as it spreads away. At the East Pacific Rise, there is no pause. The crust is pulled apart almost as soon as it forms, staying thin, hot, and weak. Magma stays close to the seafloor. Heat escapes continuously, and the ocean floor is rebuilt again and again before it can fully settle. The contrast becomes clear when compared with the Mid-Atlantic Ridge, where plates separate far more slowly. There, the thicker, cooler crust sinks in the middle, forming a deep rift valley. Volcanic eruptions are less frequent and occur in bursts, while magma sits deeper below the surface. At the East Pacific Rise, the crust never has time to collapse or solidify, so the ridge swells upward, constantly hot, unstable, and newly formed. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. The geology of the East Pacific Rise sets the stage for a unique style of volcanism. There are no towering cones or violent explosions. Instead, long cracks split the seafloor, allowing lava to pour out in wide sheets that spread quickly before cooling into new crust. This process builds the ocean floor quietly but relentlessly. Because magma is so shallow, eruptions are frequent. Large sections of the ridge can be resurfaced in a matter of days or weeks. These events rarely make headlines, not because they are small, but because they occur thousands of meters below the ocean. By volume alone, the East Pacific Rise is among the most active volcanic regions on Earth, constantly producing new crust at a scale few places can match. Earthquakes are just as constant. Unlike subduction zones that store stress for rare, massive earthquakes, the East Pacific Rise releases stress continuously. As plates pull apart and magma rises, the surrounding rock fractures, generating frequent shallow earthquakes. Most are modest in size, but they occur in near-constant swarms that signal magma moving through the crust. These constant swarms are not signs of collapse. They are how the ridge functions, endlessly breaking and rebuilding the seafloor. Where the crust cracks and magma heats the seafloor, seawater is pulled downward into the rock. It sinks kilometers below the ocean floor, heats to extreme temperatures, absorbs metals and chemicals, and then surges back up into the cold ocean as hydrothermal vents. These vents act like chimneys, releasing energy and minerals straight from Earth's interior. Some vents, known as black smokers, eject dark, mineral-rich plumes loaded with iron and sulfur. Around them exists one of the most unexpected discoveries in Earth science: entire ecosystems that survive without sunlight. Giant tube worms, clams, crabs, and dense microbial mats gather around these vents, fueled not by photosynthesis, but by chemosynthesis, where life draws energy from chemicals released by the hot seafloor itself. These ecosystems depend on instability. Their survival requires a steady supply of heat and chemicals delivered by ongoing tectonic activity. When eruptions shift the seafloor or vents shut down, whole communities can vanish and reappear elsewhere. Life here is temporary, highly adaptive, and inseparable from geological change. The implications extend beyond Earth. These environments have become analogs for potential life on icy moons like Europa and Enceladus, where sunlight never reaches subsurface oceans. The East Pacific Rise shows that where heat, water, and chemistry intersect, life can emerge, even in places that appear completely hostile. Although hidden, the East Pacific Rise plays a critical role in regulating the planet. It is one of the primary pathways through which Earth loses internal heat. That heat transfer influences ocean circulation, water chemistry, and even long-term climate stability. As hydrothermal fluids circulate through the crust, they alter seawater chemistry by removing some elements and adding others. Over millions of years, this process helps regulate the composition of the global ocean. The ridge also shapes seafloor topography, which in turn guides deep ocean currents that distribute heat and nutrients around the planet. In this sense, the East Pacific Rise is a planetary regulator rather than a localized feature. Its influence is subtle and slow from a human perspective, but essential on geological timescales. Without systems like it, Earth's internal heat would be trapped, oceans would behave differently, and the surface environment that supports life would not exist in its current form. The East Pacific Rise has been active for tens of millions of years, continuously reshaping the Pacific Ocean basin. Over geological time, its segments have shifted, reorganized, and migrated. Entire sections of ocean floor have been created, split apart, and carried away on tectonic plates, preserving a record of seafloor spreading in magnetic patterns locked into the rock. Modern observations reveal that the ridge remains just as dynamic today. Over the past few decades, instruments have detected frequent volcanic eruptions, seismic swarms, and rapid changes in the seafloor. In some cases, scientists have returned to previously mapped areas only to discover fresh lava where none existed before, clear evidence that major events had occurred without being noticed. Seismic data shows that magma can force its way into the crust over just days, fracturing rock and triggering earthquake swarms. In certain episodes, sections of the seafloor have risen or shifted by meters within weeks. This is not unusual behavior, but the normal rhythm of a fast-spreading ridge. What makes this unsettling is how easily these changes escape detection. Large portions of the East Pacific Rise remain unmonitored, meaning much of its activity is only understood after it has already happened. The East Pacific Rise is not a direct source of megathrust earthquakes or tsunamis. Activity here occurs along a spreading boundary far from land and does not produce the sudden vertical seafloor movement needed to generate large tsunamis. But its importance lies in how stress can travel outward through connected tectonic systems. Major transform faults that cut across the ridge, such as the Blanco Transform Fault, Clipperton Transform Fault, and Galapagos Transform Fault, act as mechanical bridges. Changes in stress along the East Pacific Rise can be transferred along these faults toward nearby subduction zones, including the Middle America Trench and the Peru-Chile Trench. It is these subduction zones, not the ridge itself, that are capable of producing megathrust earthquakes and tsunamis. If stress conditions there are altered or pushed closer to failure, populations along the Pacific margin of Mexico, Costa Rica, Ecuador, and Peru could ultimately face the consequences. The danger is indirect, but in tectonics, indirect connections are often the most dangerous ones. Monitoring a system as vast and remote as the East Pacific Rise remains one of Earth science's greatest challenges. Scientists depend on seafloor seismometers, autonomous underwater vehicles, and occasional submersible missions to piece together what is happening along the ridge. New tools, such as fiber optic sensing along undersea cables, are beginning to provide real-time views of seismic activity and crustal movement. Even so, these advances cover only a fraction of the system. Thousands of kilometers of ridge remain unmonitored, and operating instruments in the deep ocean is costly, complex, and technically demanding. As a result, many discoveries still come after major events have already occurred. Preparedness here is not about evacuation or early warnings. It is about understanding how fast-spreading ridges work, how heat and stress move through the planet, and how subtle changes can influence wider ocean systems. Looking ahead, the East Pacific Rise will continue doing what it has for millions of years, creating new crust, releasing Earth's internal heat, and reshaping the planet from below the Pacific, quietly, relentlessly, and far beyond human sight.